Welcome to yet another session on AI inference. In today's talk, we'll understand what AI inference is, how it's different from training. We'll try to understand the transformation pipeline whenever the data is being sent to the LLM, how it is being digested by the LLM models, and how the inference is being done. We'll talk about what are the operational costs that comes into picture and why inference is memory bound and not compute bound. We'll talk about what options do we have, and we'll talk about the bottlenecks and the pros and cons for same. For illustration, we can take VLLM as a reference, this being an open source inference engine. We'll talk in detail how KV cache works and why memory in terms of KV cache turns out to be a relevant and a very critical aspect of understanding AI inference that will help us to conclude on to decide on the infrastructure and the ROI that comes with the product inception of AI. We'll understand through the numerous slides. We'll try to cover most of the aspects of AI inference and its internal process with respect to tokenization. We'll talk about the latency from the user perspective called time for first token generation. We'll talk about the prefill mechanism, and we'll talk about the KV cache, that's key value cache. We'll try to understand what are the challenges we see in the future when we talk about operational cost incur by deploying the LLM model on scale for the enterprise. So let's hop on to the details in the forthcoming slides. We need to understand why the talk matters first of all before we deep dive into the detail. We need to understand how training is something that's not the inference. As we understand, large language models are no longer in experimental stage. They are becoming the fundamental part for any modern AI system. At the real world scale, the biggest expense is coming in running the model, but not in training the same. We understand the inference is not good as same as training. Training has been already mastered and we are ready with many use cases, but the issue is something comes with inference which is still untamed. Now, if we understand how the autoregressive inference basically works and what do we infer from them. The language models doesn't produce full sentence at a once, means the models generate text one word or a piece at a time, and even new pieces based on everything that came before it. Something like we get the input, it gets fed to the model and generates the output token, and it again gets append and we get the same loop getting repeated. So the implication that comes in picture is like we get the latency gets multiplied because the generation is not parallel, it keeps on adding subsequently. So each step must wait for the last, making throughput and latency highly sensitive here. If we talk about the inference phases, most of the people think that inference time is only about how fast we generate the output tokens, but basically the prefill phase, which is when the model first digests the full prompt, can be much more costly instead. Prefill processes the entire input at once. Decode only begins after the same and works token by token. This means for any long prompt, your latency isn't from generation though, it's from the setup itself. Understanding this is a key to conclude on the real-time system design and user experience. Just to repeat here, prefill is something when we are ready with the entire prompt. Our model is ready to process the entire prompt being fed to it as an input. Decode is something that is done after prefill completes and it's done one by one token at a time. And the reason. Now, if we talk about how the latency compounds in the LLM inference. Inference latency is deceptive because even with the high throughput numbers, users may experience long delays because the LLM generates sequentially. Each token must wait for the last one to finish. This means how fast we can generate each token. When you have outputs of hundreds of tokens, this feedback loop adds up fast, and that's where the real system gets trained. So if we break down it's why the token actually adds up, we see each token waits on the last Means, unlike the batch process where the inference waits for each token to complete before next begins, it's multiplying the whole total delay here itself. So long outputs eventually means it's a long waits. And in other words, we can say if the model is holding a long context window, long waits are associated with the same. And eventually this causes a hit on the high throughput because we still have to yield with the high latency because there is a serial generation of as a bottleneck because the token are being generated in a sequence. To keep it simple, we can say how the flow goes. The raw text is being fed to the model. It gets tokenized, means converted to numerical representation, or we can say numerical IDs, then gets transferred into the embedded vectors. Now, when the embeddings are being something that's works as an input to the transformer and the machines, or we say where the compute happens, the GPU, there the matrix size gets scaled with the prompt length because the GPUs understand the matrices, and longer the context window, the longer it takes for the computation to conclude. Now, if we have to understand the transformation pipeline, we can simply break it into three phases where we get the text, it gets converted to token. That is something the machine or the machine learning models or LLM model per se we understand by converting text to numerical representation. Eventually, that gets transferred to matrix representation that the GPU understands. It's a matrix assembly at GPU. So we say tokens are packed into the matrices and thus enables processing by transformer layers. The series basically, as we said, starts with the tokenization and conclude at the GPU stage. This transformation pipeline is basically hidden from most users, but it's a fundamental foundational understanding for getting an idea on why the inference costs a lot. If we see token by token how the LLM inference loop is defined, what is the reason that each token depends on the history? So if we talk about the same, we get a fair idea that before inference even actually begins, the model has to convert all human read text into the something that the system can compute with. So that the process starts with tokenization, wherein the text fed is being converted into numerical IDs that the system understands, machine understands. But the real magic happens at the embeddings because each token ID get mapped to the vectors, usually hundreds or thousands of dimensions. As we just said in the previous slide, it's n-dimensional space. The vectors are then batched into matrices, which are what actually gets passed into model on the GPU. Now we need to understand how prompt is different from the output memory. When we talk about memory in LLM inference, there is critical distinction between the two, prompt and the output. The prompt is encoded once during prefill and then reused. It's read many times but doesn't get changed. However, the output is dynamic because with each new token, the output grows and so does the memory load. This affects key structures like the KV cache, which scales with the sequence length, and in long responses, the model's memory consumption balloons not for the computation but for storing and referencing everything generated so far. This growing overhead defines memory bound workloads. The process of generating the output leverages KV cache, that memory where the representation or the output of previous sequence is maintained, and it grows over with the time and hence eventually cause the pressure on the inference process. So as we have already understood now, longer the GPU is, longer the context for your user query is, so longer is the GPU stress. What does that mean? That means that every token in the prompt becomes a part of large matrix that's being passed to the transformer model at GPU. The longer the prompt, the larger the matrix that GPU need to work with, and they aren't small. They are basically the high dimensional and must be stored in GPU memory only. So if you now add attention, means each token attends over the entire prompt. The memory cost scales with the prompt length. In long context user cases, think multi-turn chat or retrieval augment generation. This can overwhelm GPU. It's not just about the compute anymore. Memory is like choke point. So longer the context, longer the pressure on the memory maintenance. As we see here in the diagram itself, in the slide, sorry. So it's like more is attention, more is the memory, because the self-attention layer compute over all the prompt tokens. And the same process is amplified across all the tokens, and hence the memory gets amplified. Well, hopping on to transformation attention machines, like how terms query, key and value works. Considering we are generating a long sentence, 100 of size 100 tokens, without optimization, the model would reprocess all previous tokens at each step. The KV cache prevents this. Instead of recomputing attention from scratch, the model stores previously computed keys and values. And during generation, it only needs to query for the new token, so it simply compare it with the cached keys. And the foundation, this is basically the foundational to performance. Without it, transformation inference won't scale, because caching comes with a trade-off, especially in memory usage, and that's what we are going to explore in the next slide though. How KV cache is an acceleration for attention, reusing past keys and values. What exactly that means? KV cache, as we just discussed, is one of the way how we can reuse the previously stored keys and values, so we eliminate the redundant calculation for the attention to do from scratch. This improves the performance basically. Now, if we talk about the memory cost associated, we see since, as we discussed, the cache will grow with the context. So itself can surprise the model size. That is also a possibility, because if it's span across all the different hidden layers, it might overshoot the size of model itself, and thus what we can infer is like we are bounded by the memory but not the compute. So limitation that's come in picture because of inference is due to memory saturation. Now, considering if you have to scale the same thing and we have to schedule the inference basically at a scalable level, how we can leverage the chunkified prefill and we can request the interleaving process. LLM inference doesn't happen in isolation basically. The production systems handle many requests simultaneously, but each one has its own latency profile, so the input size and the output time. So the naive scheduling leads to waste of GPU time, because we can't afford to have a GPU be in an idle state. So idle gaps when one long prompt blocks everything. So the chunk prefill breaks the prompt basically into small segments and interleaves work with others. It's like we are not waiting for one of the prompt to get concluded, but we reuse the memory basically in the segments. And this art of GPU scheduling, but not a model design and not a kernel tuning, but simply a smart orchestration. This is very essential for the throughput at scale. So if we talk about the invisible ways that we see, why actually the naive inference starves the utilization, why there is a gap. There is no work is being done, so This is something that keeps on adding in LLM inference very fast. And that too when we are serving multiple requests with different prompts and output ends. So the naive batching causes some slots to go idle early and adds the latency in the token generation, and eventually we are wasting the GPU cycles, often invisibly. So the time for first token is basically, it measures how quickly we get the first output once the prefill is done. And this is something directly dependent on the prefill process. So the latency basically comes into picture at the stage of prefill itself, and specifically when we have a long prompts. TensorRT LLM is one of the optimization scale that is done by the NVIDIA, and VLLM as an open source inference engine also supports the same. These are the basic the CUDA libraries. That's out of the context of the current talk. We'll be taking it separately. But just to give a high level understanding, like Triton Inference Server is also one of the very well accepted inference engine by NVIDIA. So we can talk about the prospects of the precision and quantization as well, wherein if we lower the precision, we get the fastest inference because we are reducing the precision from F16 to F8 FP. So this is eventually what was the idea behind this talk. So what we eventually have the takeaways is we need to understand the whole cycle of inference, and not only from the perspective of how fast we get the output, but how fast the very first token is generated, how the KV cache comes into picture, and what are the different approaches we can take wherein we can leverage the idle cycle of the GPU. Now this is something that is being addressed by most of the inference engines. We can consider VLLM as one of the open source inference engine in our next talk. I hope it was a good walkthrough. Thanks for being there. Thank you very much.